Okay. So let us consider these three equations, these three linear equations in three unknowns. The unknowns are x1, x2 and x3, the coefficients 1, 1, 1, 2, 1, 3, 3, 4 and minus 2. Okay. So this is our three equations in three unknowns. Let us give ourselves about half a minute to think about how to have a matrix representation of this equation and how to have how to solve these particular equations. Okay. Okay. So let us talk about the matrix notation for these particular equations. So we are going to write it in form of Ax equal to b. The matrix A is going to be 1, 1, 1 in the first row. In the second row we will have 2, 1, 3, and in the third row we will have 3, 4, minus 2. For matrix for the vector B we will have 4, 7, 9 as the vector B. Okay. So now we have the matrix A and the vector B, and then we will try to solve these equations using the Gauss elimination process. Before that we will try to solve it using the algebraic method that we typically use. So the first step that we will do is take equation number 2, okay, and add minus 2 multiplied by equation number 1, and we will take equation number 3 and do minus 3 multiplied by equation number 1, okay, and they will give 0 x1 plus 1 minus 2, that is minus 1 x2 plus 3 minus 2, that is x3 plus 1 x3 equal to 7 minus 4, that is 7 minus 8, that is minus 1. We will again have 0 x1 plus 4 minus 3, that is 1 x2 plus minus 2 minus 3, that is plus minus 5 x3 equal to 9 minus 12, that is going to be equal to minus 3. So now one equation is going to be equation number 1, this is going to be our new equation number 2, this is going to be our new equation number 3. Okay. So next what we will do is we will add these two equations and replace the last equation with that particular sum. So we will do this as equation 5 plus 1 multiplied by equation 4, and when we actually do that we will get this as 0 x1 plus 0 x2 plus minus 5 plus 1, that is minus 4 x3 equal to minus 3 minus 1, that is going to be equal to minus 4. So now we have the three equations in three unknowns. The first equation is 0 x1 plus 0 x2 minus 4 x3 equal to minus 4. Back substituting we will get x3 equal to 1. Next we will substitute x3 equal to 1 in this particular equation and we will be able to get x2 equal to 2 over here, and x3 equal to 1 and x2 equal to 2 will actually give us x1 into this equation, and that will actually give us x1 equal to x1 equal to 1 in this particular equation. Okay. This is how we go about solving. What I have done so far are the steps that will be involved in getting a lower triangular matrix for the matrix A. Keep in mind the same row operations that we use for the matrix A, we are applying the same row operations for the matrix B as well. So the first point is that Gauss elimination step, when we have n equations in n unknowns, will involve n minus 1 steps. Okay. In each step we have multiple sub steps. Okay. What we will do in ith step, we will use the ith row okay, we will use the ith row to make the coefficients of xi in all equations in row I plus 1 up to row n equal to 0 to obtain okay, we will use ith row to obtain the coefficients a I comma j for where j is greater than I equal to 0. So what we mean by that is the first step is to construct or the 0th step is to construct the matrix AB, which will be 1 1 1 2 1 3 3 2 minus 2 sorry 3 4 minus 2 and our B is 2 7 9. Okay. Step 1 will involve making this and this element as 0. So step 1 is use R1 okay, use R1 to obtain zeros in column 1 in row 2, row 3 and so on up to row n. Okay. So what we will do is R1 or sorry our R2 is going to be our original R2 plus some coefficient alpha 2 1 multiplied by R1, and likewise we will have R3 as R3 plus some coefficient multiplied by R1. Okay. I will write it in this particular form. Okay. So what did we do over here? If we go back to this equation, what we did is we multiplied it with minus 2, and in the equation 3 we multiplied with minus 3, and we have multiplied equation 1 with minus 3 and added that to equation 3. Okay. So what we do over here is we multiply the row 1 with negative 2, which I will write this as minus 2 divided by 1, and this I will write this as minus 3 divided by 1. Okay. And when we do that, the next matrix AB that we will get is we will get 1 0 0 1 1 2 over here. So this will be negative 2, this term will be 1, this term will be equal to negative 1. Okay. And this of course is 0, 4 minus 3 is 1, minus 2 minus 3 is minus 5, and then 9 minus 2 is 1. Okay. And if we compare it with the equations that we got, the new equation was 0 minus 1 1 minus 1 0 1 minus 5 minus 3. So so we actually do oh sorry, this should be minus 1, 0 minus 1 1 minus 1 0 1 minus 5 1 is actually what we get as our matrix A after the first row operation. Okay. Keep in mind what we have done over here is multiplied this R1 with ratio of coefficients. Okay. So, alpha 3 1, because we are changing the row 3 with by using row 1, alpha 3 1 is going to be equal to negative a 3 1 divided by a 1 1. Likewise, what we have over here is alpha 2 1 is going to be negative of 2 divided by 1, which is a 2 1 divided by a 1 1. Okay. So, this is what we did as step 1. In step 1 we used row 1 in order to make zeros in all the in the first column below the first row. Okay. So, in step 2 we will use the row 2 in order to make the coefficients in column 2 equal to 0 below row 2 using the row operations. So, the result of step 1 we had this particular matrix, and in order to make 0 over here we have to multiply with negative of the ratio of the coefficients. So, minus 1 divided by minus 1 is what we have to multiply it with. In other words, we just have to add those two equations. So, what we have to do is we have to do R3 plus minus 1 divided by minus 1 multiplied by R2. Keep in mind this is ratio of coefficients. Okay. So, when we do that, what we will get is we will get 1 1 1 2 in the first row, the first row is unchanged, 0 minus 1 1 minus 1, the second row is unchanged. We will get this as 0 0 minus 4 and 0 over here. Okay. So, that is what we are actually going to get when we do addition of these two rows. I think I have probably made a mistake over here. So, when we do this row operation, this will be 0 minus 1 minus 2 is minus 1, 3 minus 2 is plus 1, 7 minus 4 is plus 3. And 0 1 minus 5 and 3 times yeah and 1. Okay. So, this is what we have we ought to be getting. So, we will get 0 minus 1 1 3 and 0 0 4 4. Okay. So, this is what we will get. So, in terms of this matrix A that we have over here, this is now reduced to a lower triangular matrix. Okay. And then we will use the back substitution and in the back substitution step we will have x3 going to be equal to 1. We will substitute this x3 equal to 1 over here, x2 equal to minus 2, we substitute x2 equal to minus 2 and x3 equal to 1 over here, and we will get x1 equal to 1 in this particular equation. Okay. So, this is how we will actually get the final solution. So, in back substitution we will use 4x3 equal to 4, which will give us x3 equal to 1, and then we will substitute x3 into this equation, and then we substitute x2 and x3 into this equation, and we get the overall solution. So Gauss elimination will consist of n minus 1 steps. So we, let us say that we have an n by n equations in n unknowns. So we have the matrix A and the vector B bar, and if instead of one equation, if we had n more, if we had more sets of equation in terms of Ax bar equal to B1 bar and Ax bar equal to B2 bar, we can solve both these equations simultaneously by creating a matrix A B1 B2. So if we had Ax bar equal to B1 bar as one set of equations and Ax bar equal to B2 bar as other set of equations, and we had to solve this set of equation independently of this set of equations, the way we can go about solving is create a matrix A B1 B2, okay, and then apply the all the row transformations to this particular matrix, and we will be able to indeed solve this two sets of equations simultaneously. This is going to be very useful when we are going to consider inversion of a matrix, that I am going to consider in the next lecture in this particular module, okay. So we have Ax equal to B. Step 1 is going to be use R1 to get zeros in column 1, row 2 to n, okay, and how we do that is Rj is going to be equal to Rj plus alpha j comma I or alpha j comma 1 R1, where alpha j1 is the ratio of the coefficients, and if we go back and look over here, the ratio of the so we had R2 given as R2 plus negative of alpha A21 divided by A11, okay, alpha 21 was negative of A21 divided by A11. Likewise over here alpha 31 was equal to negative of A31 divided by A11. In general alpha j1 is going to be equal to negative of aj1 divided by a11, okay. So this is what we are going to write, aj1 is negative of a j1 divided by a11, okay. So once we have this particular step, as a result of this step we are going to get, so we will start off with the original matrix A11, A12, A13 up to A1n and then B1, so on and so forth. So our first row remains unchanged, so we will have A11, A12, A13, so on up to A1n B1. Our second row is going to be, we will get 0 at this location, we do not have to compute that, simply by using aj1 divided by a11 we are going to get 0 over there. So we will have 0 over here, this will be a22 after the first operation, a23 after the first operation, and so on up to a2n after the first operation, b2 after the first operation. Likewise we will change our row 3 or row 4 or row 5 and so on. So we will immediately get 0 over here, we will have a32 after the first operation, a33 after the first operation, and so on up to a3n after the first operation and b3 after the first operation, and so on up to the nth row. Again in the nth row we are going to get 0 over here, okay, and over here we will get a n2 after the first operation, a n3 after the first operation, and so on up to a nn after the first operation, followed by Bn after the first operation. Okay. So, this is going to be the step 1 of the Gauss elimination step. In step 2 of the Gauss elimination step, we will use row 2 to get zeros in column 2. So, that is going to be our next step. Okay. So, the step 2 is going to be to use row 2 for row elimination. So, we want to get 0 over here, here and so on up to this point, and therefore, we are going to multiply Rj with an appropriate coefficient multiplied by R2. So, Rj will be Rj plus alpha j2 multiplied by R2, and in this particular case alpha j2 is going to be, for example, over here it is going to be negative of A321 divided by A221, negative of A421 divided by A221 and so on up to negative of AN21 divided by A221, or in general alpha j2 is going to be equal to negative A j2 divided by A22. Okay, and so on up to step I is going to be use ith row for row elimination. Okay. So, R I plus 1 is going to be equal to R I plus 1 plus alpha I plus 1 comma I R I, where alpha I plus 1 comma I is going to be equal to minus A I minus 1 I plus 1 comma I divided by A I minus 1 I comma I, because this has been obtained after I minus 1 row operations. In fact, we will have 1 as a subscript superscript over here, and we do this for I plus 1, we do this for I plus 2 and so on. So, we can replace this I plus 1 with just j over here, and so all the I plus 1s will replace by j. So, this is what we end up doing. Now, if we consider this what we do in step 2 and what we do in step I, we have Rj over here where j is going to be greater than 2, in this case j is going to be greater than I. Okay. So, let me write the algorithm. Okay. And again I am going to very roughly write the algorithm, not in a standard form. Okay, so we will do let I go from 1 to n minus 1, because we are doing those row operations using row 1, row 2, row 3 up to row n minus 1. We are not using the row n minus 1th row to do any row operation. So, which means in step I for is going to involve for j going from 1 from j going from I plus 1 to n, that means the row I plus 1, row I plus 2, row I plus 3 and so on, we need to get Rj, or we need to replace Rj with Rj plus alpha j comma I Ri, where alpha j comma I is going to be equal to negative A j comma I divided by Aii. Okay. So, that is what we have in the ith step. Keep in mind this is not one single operation, but this itself involves multiple operations. So, if we were to expand this operation, we will have, so Rj is the jth row, okay, in the jth row, for the first column we will have it 0, second column we will have 0, and so on up to the j minus 1th column we will have 0. In the jth column we will definitely get 0 because we are using rj to make that particular in the ith column we will definitely get a 0 because we are using ri in order to get 0 in that column. So we will have for k going from I plus 1 to n plus 1, where the n plus 1 is for the bth for the vector b. Okay. In this particular case we will have a, so we are looking at the jth row, okay, and all the columns after the column I. So we will go for a j comma k is going to be equal to a j k plus alpha j I multiplied by I multiplied by a. So it is the ith row, so we will have sorry, it is the jth row, so we will have so I am sorry, we are going to use the ith row in order to make zeros in the jth row ith column, and this will change all the other columns as well. So this is going to be a I comma k, okay, because this is going to be the column kth, the kth column, and we are going to use the row I in order to change that particular variable. So this is very roughly what algorithm we are going to follow. Okay. So what we have covered so far essentially is the background behind the Gauss elimination, and very briefly looked at the algorithm for Gauss elimination. In the next lecture I will take off from the algorithm for Gauss elimination and try to compute how much amount of computational effort the Gauss elimination step is going to require. Next I am going to talk about the back substitution itself, and finally I will finish off with two other methods, specifically the Gauss-Jordan method and LU decomposition. So that is basically what we will cover in the next lecture of this module. Okay, thank you.